In this part 2 of the 2 lectures, I'll show the fallacies in the reasoning leading to the paradoxes in the current theory of infinity, and will show that we are able to rectify those paradoxes by proper reasoning. Again, you can download the book from this site. I showed you many paradoxes in the current theory of infinity in part 1. There are other famous paradoxes, for example, Banach-Tarski paradox, which I did not discuss. But there are enough paradoxes already. One of the most troubling paradoxes was infinitely many sizes of infinity, leading to another paradox that the self should be greater than itself. The next video, downloaded from Vsauce, is 24 minutes long, but will show this paradox very clearly.
Hey Vsauce, Michael here. What is the biggest number you can think of? A Google? A Googleplex? A millinillion-olplex? Well, in reality, the biggest number is 40. Covering more than 12,000 square meters of Earth, this 40, made out of strategically planted trees in Russia, is larger than the battalion markers on Signal Hill in Calgary, the 6 found on the Faven badges in England, even the mile of pi Brady unrolled on Numberphile. 40 is the biggest number on Earth in terms of surface area. But in terms of amount of things, which is normally what we mean by a number being big, 40 probably isn't the biggest. For example, there's 41. And then there's 42, and 43, a billion, a trillion. You know, no matter how big of a number you can think of, you can always go higher. So there is no biggest last number. Except infinity? No. Infinity is not a number. Instead, it's a kind of number. You need infinite numbers to talk about and compare amounts that are unending. But some unending amounts, some infinities, are literally bigger than others. Let's visit some of them and count past them. First things first, when a number refers to how many things there are, it is called a cardinal number. For example, 4 bananas, 12 flags, 20 dots. 20 is the cardinality of this set of dots. Now, 2 sets have the same cardinality when they contain the same number of things. We can demonstrate this equality by pairing each member of one set 1-to-1 with each member of the other. Same cardinality, pretty simple. We use the natural numbers, that is 0, 1, 2, 3, 4, 5, and so on, as cardinals whenever we talk about how many things there are. But how many natural numbers are there? It can't be some number in the naturals because there'd always be 1 plus that number after it. Instead, there's a unique name for this amount: Aleph Null. Aleph is the first letter of the Hebrew alphabet, and Aleph Null is the first, smallest infinity. It's how many natural numbers there are. It's also how many even numbers there are, how many odd numbers there are. It's also how many rational numbers, that is, fractions, there are. That may sound surprising, since fractions appear more numerous on the number line, but as Cantor showed, there's a way to arrange every single possible rational such that the naturals can be put into a 1-to-1 correspondence with them. They have the same cardinality. Point is, Aleph Null is a big amount. Bigger than any finite amount. A Googleplex? A Googleplex factorial to the power of a Googleplex to a Googleplex squared times Graham's number? Aleph Null is bigger. But we can count past it. How? Well, let's use our old friend, the supertask. If we draw a bunch of lines and make each next line a fraction of the size and a fraction of the distance from each last line, well, we can fit an unending number of lines into a finite space. The number of lines here is equal to the number of natural numbers that there are. The two can be matched 1 to 1. There's always a next natural, but there's also always a next line. Both sets have the cardinality Aleph null. But what happens when I do this? Now, how many lines are there? Aleph null plus 1? No. Unending amounts aren't like finite amounts. There are still only Aleph null lines here because I can match the naturals 1 to 1 just like before. I just start here and then continue from the beginning. Clearly, the amount of lines hasn't changed. I can even add 2 more lines, 3 more, 4 more. I always end up with only Aleph null things. I can even add another infinite Aleph null of lines and still not change the quantity. Every even number can pair with these and every odd number with these. There is still a line for every natural. Another cool way to see that these lines don't add to the total is to show that you can make this same sequence without drawing new lines at all. Just take every other line and move them all together to the end. It's the same thing. But hold on a second. This and this may have the same number of things in them, but clearly there's something different about them, right? I mean, if it's not how many things they're made of, what is it? Well, let's go back to having just one line after an Aleph null sized collection. What if, instead of matching the naturals 1 to 1, we insist on numbering each line according to the order it was drawn in? So we have to start here and number left to right. Now, what number does this line get? In the realm of the infinite, labeling things in order is pretty different than counting them. You see, this line doesn't contribute to the total, but in order to label it according to the order it appeared in, well, we need a set of labels, of numbers, that extends past the naturals. We need ordinal numbers. The first trans-finite ordinal is omega, the lowercase Greek letter omega. This isn't a joke or a trick. It's literally just the next label you'll need after using up the infinite collection of every single counting number first. If you got omegath place in a race, that would mean that an infinite number of people finished the race, and then you did. After omega comes omega plus 1, which doesn't really look like a number, but it is, just like 2 or 12 or 800. Then comes omega plus 2, omega plus 3. Ordinal numbers label things in order. Ordinals aren't about how many things there are. Instead, they tell us how those things are arranged. Their order type. The order type of a set is just the first ordinal number not needed to label everything in the set in order. So, for finite numbers, cardinality and order type are the same. The order type of all the naturals is omega. The order type of this sequence is omega plus 1, and now it's omega plus 2. No matter how long an arrangement becomes, as long as it's well ordered, as long as every part of it contains a beginning element, the whole thing describes a new ordinal number. Always. This will be very important later on. It should be noted at this point that if you are ever playing a game of who can name the biggest number, and you're considering saying omega plus 1, you should be careful. Your opponents might require the number you name to be a cardinal that refers to an amount. These numbers refer to the same amount of stuff, just arranged differently. Omega plus 1 isn't bigger than omega, it just comes after omega. But Aleph null isn't the end. Why? Well, because it can be shown that there are infinities bigger than Aleph null, that literally contain more things. One of the best ways to do this is with Cantor's diagonal argument. In my episode on the Banach-Tarski paradox, I used it to show that the number of real numbers is larger than the number of natural numbers. But for the purposes of this video, let's focus on another thing bigger than Aleph Null, the power set of Aleph Null. The power set of a set is the set of all the different subsets you can make from it. For example, from the set of 1 and 2, I can make a set of nothing, or 1, or 2, or 1 and 2. The power set of 1, 2, 3 is the empty set, 1, and 2, and 3, and 1 and 2, and 1 and 3, and 2 and 3, and 1, 2, 3. As you can see, a power set contains many more members than the original set. 2 to the power of however many members the original set had, to be exact. So, what's the power set of all the naturals? Well, let's see. Imagine a list of every natural number. Cool. Now, the subset of all, say, even numbers would look like this. Yes, no, yes, no, and so on. The subset of all odd numbers would look like this. Here's the subset of just 3, 7, and 12. And how about every number except 5? Or no number except 5? Obviously, this list of subsets is going to be, well, infinite. But imagine matching them all 1-to-1 with a natural. If, even then, there's a way to keep producing new subsets that are clearly not listed anywhere here, we will know that we've got a set with more members than there are natural numbers. A bigger infinity than Aleph Null. The way to do this is to start up here in the first subset and just do the opposite of what we see. 0 is a member of this one, so our new set will not contain 0. Next, move diagonally down to 1's membership in the second subset. 1 is a member of it, so it will not be in our new one. 2 is not in the third subset, so it will be in ours, and so on. As you can see, we are describing a subset that will be, by definition, different in at least one way from every single other subset on this Aleph Null-sized list. Even if we put this new subset back in, diagonalization can still be done. The power set of the naturals will always resist a 1-to-1 correspondence with the naturals. It's an infinity bigger than Aleph Null. Repeated applications of power set will produce sets that can't be put into 1-to-1 correspondence with the last. So it's a great way to quickly produce bigger and bigger infinities. The point is, there are more cardinals after Aleph Null. Let's try to reach them. Now remember that after omega, ordinals split, and these numbers are no longer cardinals. They don't refer to a greater amount than the last cardinal we reached, but maybe they can take us to one. Wait, what are we doing? Aleph Null? Omega? Come on, we've been using these numbers like there's no problem. But if at any point down here, you can always add 1. Always. Can we really talk about it, this endless process, as a totality and then follow it with something? Of course we can. This is math, not science. The things we assume to be true in math are called axioms. And an axiom we come up with isn't more likely to be true if it better explains or predicts what we observe. Instead, it's true because we say it is. Its consequences just become what we observe. We are not fitting our theories to some physical universe whose behavior and underlying laws would be the same whether we were here or not. We are creating this universe ourselves. If the axioms we declare to be true lead us to contradictions or paradoxes, we can go back and tweak them or just abandon them altogether, or we can just refuse to allow ourselves to do the things that cause the paradoxes. That's it. What's fascinating, though, is that in making sure the axioms we accept don't lead to problems, we've made math into something that is, as the saying goes, unreasonably effective in the natural sciences. So to what extent we're inventing all of this, or discovering it, it's hard to say. All we have to do to get omega is say, let there be omega, and it will be good. That's what Ernest Zermelo did in 1908 when he included the axiom of infinity in his list of axioms for doing stuff in math. The axiom of infinity is simply the declaration that one infinite set exists, the set of all natural numbers. If you refuse to accept it, that's fine. That makes you a finitist, one who believes only finite things exist. But if you accept it, as most mathematicians do, you can go pretty far, past these and through these. Eventually we get to omega plus omega, except we've reached another ceiling. Going all the way out to omega plus omega would be to create another infinite set. And the axiom of infinity only guarantees that this one exists. Are we going to have to add a new axiom every time we describe Aleph Null more numbers? No. The axiom of replacement can help us here. This assumption states that if you take a set, like say the set of all natural numbers, and replace each element with something else, like say bananas, what you're left with is also a set. That sounds simple, but it's incredibly useful. Try this. Take every ordinal up to omega, and then, instead of bananas, put omega plus in front of each. Now we've reached omega plus omega, or omega times 2. Using replacement, we can make jumps of any size we want, so long as we only use numbers we've already achieved. We can replace every ordinal up to omega with omega times it to reach omega times omega, omega squared. We're cooking now. The axiom of replacement allows us to construct new ordinals without end. Eventually, we get to omega to the omega to the omega to the omega to the omega, and we run out of standard mathematical notation. No problem. This is just called epsilon naught, and we continue from here. But now, think about all of these ordinals, all the different ways to arrange Aleph Null things. Well, these are well ordered, so they have an order type, some ordinal that comes after all of them. In this case, that ordinal is called omega 1. Now, because by definition, omega 1 comes after every single order type of Aleph Null things, it must describe an arrangement of literally more stuff than the last Aleph. I mean, if it didn't, it would be somewhere in here. But it's not. The cardinal number describing the amount of things used to make an arrangement with order type omega 1 is Aleph 1. It's not known where the power set of the naturals falls on this line. It can't be between these cardinals because, well, there aren't cardinals between them. It could be equal to Aleph 1. That belief is called the continuum hypothesis. But it could also be larger. We just don't know. The continuum hypothesis, by the way, is probably the greatest unanswered question in this entire subject. And today, in this video, I will not be solving it, but I will be going higher and higher to bigger and bigger infinities. Now, using the replacement axiom, we can take any ordinal we've already reached, like, say, omega, and jump from Aleph to Aleph all the way out to Aleph omega. Or heck, why not use a bigger ordinal like omega squared to construct Aleph omega squared? Aleph omega 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 omega. Our notation only allows me to add countably many omegas here, but replacement doesn't care about whether or not I have a way to write the numbers it reaches. Wherever I land will be a place of even bigger numbers, allowing me to make even bigger and more numerous jumps than before. The whole thing is a wildly accelerating feedback loop of embiggening. We can keep going like this, reaching bigger and bigger infinities from below. Replacement and repeated power sets, which may or may not line up with the Alephs, can keep our climb going forever. So clearly there's nothing beyond them. right? Not so fast. That's what we said about getting past the finite to omega. Why not accept as an axiom that there exists some next number so big no amount of replacement or power setting on anything smaller could ever get you there? Such a number is called an inaccessible cardinal because you can't reach it from below. Now, interestingly, within the numbers we've already reached, a shadow of such a number can be found. Aleph null. You can't reach this number from below either. All numbers less than it are finite, and a finite number of finite numbers can't be added, multiplied, exponentiated, replaced with finite jumps a finite number of times, or even power set a finite number of times to give you anything but another finite amount. Sure, the power set of a milli-nillion to a googolplex to a googolplex to a googolplex is really big, but it's still just finite, not even close to Aleph null, the first smallest infinity. For this reason, Aleph null is often considered an inaccessible number. Some authors don't do this though, saying an inaccessible must also be uncountable, which, okay, makes sense. I mean, we've already accessed Aleph null. But remember, the only way we could is by straight up declaring its existence axiomatically. We will have to do the same for inaccessible cardinals. It's really hard to get across just how unfathomable the size of an inaccessible cardinal is. I'll just leave it at this. The conceptual jump from nothing to the first infinity is like the jump from the first infinity to an inaccessible. Set theorists have described numbers bigger than inaccessibles, each one requiring a new large cardinal axiom asserting its existence, expanding the height of our universe of numbers. Will there ever come a point where we devise an axiom implying the existence of so many things that it implies contradictory things? Will we someday answer the continuum hypothesis? Maybe not, but there are promising directions. And until then, the amazing fact remains that many of these infinities, perhaps all of them, are so big, it's not exactly clear whether they even truly exist or could be shown to in the physical universe. If they do, if one day physics finds a use for them, that's great. But if not, that's great too. That would mean that we have, with this brain, a tiny thing a septillion times smaller than the tiny planet it lives on, discovered something true outside of the physical realm. Something that applies to the real world, but is also strong enough to go further, past what even the universe itself can contain or show us or be. And as always, thanks for watching.
In part 2, I'll show that a correct theory of infinity has only paradox 1 and 2. Other paradoxes will be shown as a logical fallacy. Again, I try to follow the advice of David Hilbert. Chapter 2-1, Paradox of Infinity. A part is the same as the whole. It is counterintuitive that a part has the same number of elements as the whole from which the part is generated, thus a paradox. However, if we define the method of one-to-one pairing as a way of comparing sizes, including infinity, then it is a paradox that we have to accept as a logical conclusion. In fact, this concept that the whole can be the same size as the part is the definition of Dedekind infinite. From the examples in chapter 1-1, Aleph null equals twice the Aleph null equals Aleph null squared. Chapter 2-2, Paradox of larger infinity. It is true that C, the size of the number of the real numbers, is larger than Aleph null, the size of the number of the natural numbers. Cantor showed that C equals 2 to the power Aleph null and 2 to the power Aleph null is larger than Aleph null. Thus, C equals 2 to the power Aleph null, which is larger than Aleph null, by Cantor's diagonal argument and Cantor theorem. Herein, I proved that C is larger than Aleph null by arithmetic argument, but also proved that 2 to the power Aleph null equals Aleph null. Thus, C is larger than 2 to the power Aleph null, which is equal to Aleph null. First, I'll have an arithmetic proof that C is larger than Aleph null. In the basic arithmetic or number theory, the property of 0 is defined as alpha plus 0 equals alpha, and alpha multiplied by 0 equals 0 for any cardinal number alpha. Thus, by the definition of 0 in the basic arithmetic or number theory, summating any number of zeros and multiplication by 0 equals 0. Thus, Aleph null multiplied by 0, which is summing zeros Aleph null times, equals 0. By definition, a point has a length. An interval in the real number line has a length. In measure theory, any open or closed interval a and b of real numbers has a length b minus a, which is consistent with our common sense. Therefore, if b is not equal to a, then the length is larger than 0. The length b minus a is called its Lebesgue measure. By definition, C is a number of points in a real number line with a length. Therefore, the sum of C number of points which have a length of 0 by definition should be greater than 0 by definition. Thus, C multiplied by 0, that is, summing zeros by C times, should be greater than 0. Thus, C is larger than Aleph null. Thus, we have a proof that C should be larger than Aleph null simply by definition of a point, a line, and rules of arithmetic and number theory. Here, you can reason that C is more of an idea or concept than an actual number, because it is not possible to have a positive real number by adding zeros or multiplying zeros in the rules and definitions of an arithmetic and number theory. I'll also show that C is not in the real number line in chapter 2-8, supporting that C is different from an actual number. Furthermore, I'll show that C is not equal to 2 to the power Aleph null. Thus, C is not just quantitatively larger than Aleph null, but qualitatively different from Aleph null, like topological dimensionality, and can only be expressed as being larger, that is, C is larger than Aleph null. Thus, arithmetic with C should be done as an idea or a concept. Relation between Aleph null and to the power Aleph null. Cantor's diagonal argument and Cantor theorem showed that 2 to the power Aleph null is larger than Aleph null. However, I'll show that 2 to the power Aleph null equals Aleph null from many arguments. Argument 1 is binary branching tree diagram. Argument 2 is arithmetic proof. And I'll show fallacies in the Cantor's diagonal argument and Cantor theorem. Argument 1. Let's suppose a binary branching tree diagram of balls as in figure. As we can number the balls in the tree diagram sequentially from top to bottom and left to right as in figure, the balls in the diagram can have a 1-to-1 pairing with natural numbers. There is no reason why we cannot continue this binary branching infinitely, and number them or one-to-one pair them with natural numbers. B. The number of balls in the tree after n steps will be Bn, which is 2 to the power n minus 1. Thus, the number of balls after Aleph null steps, B Aleph null equals 2 to the power Aleph null. And we can number them or one-to-one pair them with natural numbers. Thus, B Aleph null, which is 2 to the power Aleph null, is equivalent to the size of natural numbers, which is Aleph null. Thus, 2 to the power Aleph null equals Aleph null. Argument 2 is arithmetic proof by induction. 1. Aleph null equals Aleph null plus 1. By induction, Aleph null equals Aleph null plus I equals Aleph null plus I plus 1 leading to Aleph null plus Aleph null equals Aleph null times 2. Second, Aleph null equals Aleph null times 1 plus 1. By induction, Aleph null equals Aleph null times I equals Aleph null times I plus 1, leading to Aleph null times Aleph null, that is Aleph null squared. 3. Aleph null equals Aleph null to the power 1 plus 1. By induction, Aleph null equals Aleph null to the power I equals Aleph null to the power I plus 1, leading to Aleph null to the power Aleph null. 4. Thus, Aleph null equals Aleph null to the power Aleph null, and is larger than or equal to 2 to the power Aleph null. As I is not larger than 2 to the power I for any I, Aleph null will not be larger than 2 to the power Aleph null. Therefore, Aleph null equals 2 to the power Aleph null. I just proved Aleph null equals 2 to the power Aleph null by binary branching tree diagram method and arithmetic proof rule of induction. However, there are Cantor's diagonal argument and Cantor theorem that says 2 to the power Aleph null is larger than Aleph null. Therefore, I need to show fallacies in those arguments. In Cantor's diagonal argument, let me repeat the discussion in part 1 because this is critical. The proof starts by considering real numbers in a unit interval as the set T of all infinite sequences of binary digits. Assume that T is countable. Then we can list all elements from T in a row. But when any S1, S2, is listed as elements from T, there is always an element S of T which is constructed by choosing the ith digit complementary to the ith digit in Si, which corresponds to no Si in the listing. For example, the first digit in S1 is 0, thus the first digit of S be 1, which is complementary to 0. The second digit in S2 is 1, thus the second digit of S is 0. The third digit in S3 is 0, thus the third digit of S is 1, Then S is different from any Si in the list, different from S1 in the first digit, different from S2 in the second digit, different from S3 in the third digit, Thus, there is always an element of T which is not present in the list. This contradicts the original assumption, T being countable. Thus, T is uncountable by contradiction. Therefore, C, which is car T, which is 2 to the power Aleph null by arithmetic, is uncountable. Thus, C equals 2 to the power Aleph null, which is larger than Aleph null. But there is a fatal error in the Cantor's diagonal argument. The assumption in the proof that C is countable obfuscates the fact that T or Si is infinite. The fallacy is that you completed the listing Si when you should not. Because you cannot complete the listing Si, S cannot exist. There is a way to list all elements of T which shows it evident that S cannot exist. This is an ordered listing of real numbers in binary digits in a countable but infinite binary branching tree diagram in a horizontal direction. Start from the left with two balls and have 0 and 1 each. Repeat this numbering iteratively. Then, all combinations of zeros and ones will be listed in Si. Listing is ordered, infinite, and countable. If you want to make the diagonal number S, the complementary sequence will be found in the bottom. The first digit of S1 is 0, thus the first digit of S will be 1. The second digit of S2 is not 1 because there are many more numbers on the right with 0 in the second digit. Thus, the second digit in S2 will be 0. Thus, the second digit in S will be 1. What about the third digit in S3? Will it be 1? No, there are many more numbers with zeros on the right with a 0 in the third digit. Thus, the third digit in S3 will be 0. Thus, the third digit in S will be 1. This will continue infinitely. Thus, we will never be able to complete making S because the listing is infinite. Therefore, the diagonal argument does not hold in infinity. Cantor tried to show C equals car T, which is 2 to the power Aleph null, that is larger than Aleph null. But Cantor's diagonal argument does not hold in infinity, thus we fail to show 2 to the power Aleph null is larger than Aleph null. Is there a good way to one-to-one pair real numbers and natural numbers? In order to have a successful one-to-one pairing, listing should be ordered and complete. Cantor was able to prove that rational numbers have the same cardinality as natural numbers because he designed a way of listing a complete and ordered set of rational numbers. Cantor's diagonal argument was a method of contradiction, but he made a wrong assumption that listing Si was complete when it should continue to infinity. In other words, he fell into the trap of the largest natural number n. His listing of Si was neither complete nor ordered. When listing of Si was done complete and ordered, it was evident that S cannot exist in infinity. Is there a systematic way of listing a complete and ordered set of real numbers? Yes, this is how we can make a complete and ordered set T of real numbers. Let R be a sequence of real numbers in an open unit interval, then take the midpoint number within the interval. Then take the midpoint numbers within each sub-intervals. By iterating Aleph null times, a sequence T Aleph null of midpoint numbers, which is a set of binary digits, will be generated with a size of 2 to the power Aleph null. And then have the elements in T fill this binary branching tree diagram from top to bottom and left to right, so that the balls will represent the elements in T. This is a number expressed in binary number system. We discussed in argument 1 that the balls can be one-to-one paired with natural numbers. Thus, this diagram shows that the set T, which is a set of real numbers expressed in infinite sequences of binary digits, can be one-to-one paired with natural numbers. We are able to have successful one-to-one pairing between T and natural numbers because T, which is the real numbers expressed in infinite sequences of binary digits, is listed in an ordered way like we did for rational numbers. Thus, this proves car T equals 2 to the power Aleph null equals Aleph null. Does it mean that real numbers have the same cardinality as natural numbers? No. We have to remember that pairing is between natural numbers and the real numbers expressed in infinite sequences of binary digits. Cantor considered that real numbers are the set T of all infinite sequences of binary digits. It may seem obvious that real numbers can be written as an infinite sequence of binary digits. Cantor took it for granted infinite as Aleph null in the proof. However, we need to know what infinite means exactly because there are at least two different sizes of infinity, Aleph null and C. I've shown that C is larger than Aleph null and that Aleph null equals 2 to the power Aleph null in the above discussion. Therefore, C is larger than Aleph null, which equals to the power Aleph null, which is car T. Thus, it follows that not all real numbers can be written in binary representation of digit length of Aleph null. This means that the length of digits of a real number should be larger than Aleph null. What does it mean digit length is larger than Aleph null? If continuum hypothesis is correct, C is a candidate. However, C is more of an idea than an actual number that defies the basic rules of arithmetic. A rational number either terminates after a finite number of digits or begins to repeat the same finite sequence of digits. Thus, rational numbers can be written in digit representation by notations such as 1/3 equals 0.333 ... which is 0.3 bar. The digit expansion of an irrational number continues without repeating. Thus, irrational numbers cannot be written in digit representation, like irrational numbers cannot be written as P over Q for any natural number P and Q. Let me summarize first before we move on further. C is larger than Aleph null by definition of a point, a line, and rules of arithmetic. Second, Aleph null equals 2 to the power Aleph null by one-to-one pairing, rules of arithmetic, and showing a fallacy in the proof of Cantor's diagonal argument. 3. C is larger than 2 to the power Aleph null, meaning that the digit length in digit representation of real numbers is larger than Aleph null. Thus, irrational numbers cannot be written in digit representation. Rational numbers can be written in digit representation by the notation rule. There is another theorem that argued 2 to the power Aleph null is larger than Aleph null, Cantor theorem. Thus, I need to show that there is a fallacy in this theorem. This famous proof of Fermat's last theorem by Andrew Wiles is 109 pages long, and there is a recent stir that ABC conjecture is finally proven. But some experts say that the author, a Japanese mathematician Shinichi Mochizuki, failed to fix fatal flaw in solution. This paper is 600 pages long. Well, both proofs are very long, so that there may be an error hiding somewhere. But the proof of Cantor theorem is just 3 lines long. How this proof can have an error? Let's look at the proof meticulously. The proof considers a subset B of PA whose element X is not an element of Fx. Because we assume surjection, a subset B has to be in the Fx when it cannot be in the Fx. Thus, this contradicts that there is a surjection. Thus, PA has larger cardinality than A. However, if B does not exist, then this logic of contradiction does not hold. Set B, whose element X is not an element of Fx, is called as Cantor's diagonal set. In infinity, where I, the number of elements, is infinite, the list of Fi has to be infinite because I is infinite. Therefore, B cannot exist because Fi continues to infinity. And in part 1, I discussed the similarity between this set B, Cantor diagonal set, in the Cantor theorem, and S in the Cantor's diagonal argument, which can be seen more clearly by changing the presence or absence of each element in the set as 1 or 0. Then Fi becomes a list of binary digits, and B becomes a number of binary digits, ith digit complementary to ith digit of the set Fi. Thus, Cantor's theorem is Cantor's diagonal argument. And as in Cantor's diagonal argument, it does not hold in infinity because the listing of Fi or Si continues and B or S cannot exist. Cantor, who defined comparing the size in infinity by one-to-one pairing, made a fatal error in assumption in Cantor's diagonal argument and Cantor theorem. He should have considered that the listing is infinite and cannot be completed. Assuming completing the listing, that is, listing all elements, is like assuming the largest natural number n. Finding a number or subset listing plus 1 after assuming the listing is complete is like constructing a larger natural number n plus 1 after assuming the largest natural number n. In this way, he was led to a wrong conclusion that there is a larger cardinality than the listing. Probably he believed that C is larger than Aleph null, and real numbers can be expressed in infinite sequences of binary digits. Thus, C equals 2 to the power Aleph null. Thus, C equals 2 to the power Aleph null and is larger than Aleph null. Therefore, I suspect he was blinded to see the error in his arguments, because they fitted so nicely into his belief, even though he was troubled by other paradoxes that follow. Therefore, Cantor's theorem does not hold in infinity. There cannot be B in infinity. There cannot be B does not mean B is an empty set. It means B does not exist. Therefore, there is no contradiction in surjection, and A and PA should have the same cardinality in infinity. Card n equals card Pn, that is, n equals 2 to the power Aleph null. Corollary of Aleph null equals 2 to the power Aleph null is as follows. That 1 was defined as card Pn, which is 2 to the power Aleph null, n becomes Aleph null. Then bet 2 is bet 1, and by induction, bet I is bet 1 for any integer I. Thus, there are only two sizes of infinity, Aleph null and C. Therefore, all the paradoxes of infinitely many sizes of infinity are resolved. And proof of continuum hypothesis should be re-examined. We have seen many paradoxes of infinitely many paradoxes, requiring elaborate schemes of making and naming large infinities by axioms, still left with the paradox of the self larger than itself. All these paradoxes will disappear like a mist in the daylight of Aleph null equals 2 to the power Aleph null. Proof of continuum hypothesis should be re-examined because the proof was done under the premise of 2 to the power Aleph null is larger than Aleph null and infinitely many infinities. This is an old arithmetic and should be revised. Blue is the revised and red is new one. Alpha over Aleph null is larger than 0, and I'll show 3 arguments. Argument 1. In the previous cardinal arithmetic, that alpha over Aleph null equals 0 is based on the following logic. For any arbitrary small epsilon larger than 0, there is n satisfying 1 over n smaller than epsilon. Because epsilon can be arbitrarily small, 1 over n becomes 0 as n becomes infinite. However, we can have the following logic. For any arbitrary large n, there is epsilon satisfying 1 over n larger than epsilon larger than 0. Thus, 1 over Aleph null is larger than 0. Argument 2 is, if alpha over Aleph null equals 0 for alpha not equal to 0, then alpha equals 0 multiplied by Aleph null. However, Aleph null multiplied by 0 equals 0 in chapter 2-2. This contradicts alpha not equal to 0. Therefore, alpha over Aleph null is not equal to 0. Argument 3 will be found in chapter 2-5 using Lebesgue measure. Here is a wrong argument for alpha over Aleph null equals 0. Let x as 1 over 3, which is 0.33 ... which is 0.3 bar, and 10x will be 3.3 bar minus 1. 3 bar minus 1 denotes infinite minus 1 repetition of 3's. Then 9x equals 3 minus 0.0 minus 1 bar 3, and x becomes 1 over 3, 1 minus 0.0 bar minus 1, 1. As x equals 1 over 3, 0.0 bar minus 1, 1 is 0. Thus, 1 over 10 to the power infinity is 0. However, the digit length infinity in the above calculation is larger than Aleph null. Thus, it does not prove that 1 over 10 to the power Aleph null equals 0. It is easy to show 1 over 10 to the power Aleph null equals 1 over Aleph null. Alpha over c equals 0 because c is a number of points in a real number line. Thus, the divided product should be a point with a length of 0. We can get the same results by dividing c on both sides of the formula c multiplied by 0 equals alpha. Alpha over 0 equals c, and this comes from the idea that the number of points in the interval is c. In chapter 2-8, I will show that c is not in the real number line. C multiplied by c, which is c squared, is larger than c from this arithmetic, and will be shown in dimensionality products in the following discussion. In generic terms, Aleph null minus Aleph null and Aleph null over Aleph null are not determined. However, in conditions where the nature of Aleph null is specified, they can be determined. For example, let Aleph null 1 as cardinality of natural numbers and Aleph nor 2 as cardinality of even numbers, then Aleph nor 1 minus Aleph nor 1 equals 0. Aleph nor 1 minus Aleph nor 2 equals Aleph nor. Aleph nor 1 over Aleph nor 1 equals 1, and Aleph nor 1 over Aleph nor 2 equals 2. One may persist that they are undetermined and we do not know the answer. This may not be a completely wrong answer, but not the best one. I'll summarize the discussion until now. Products of infinity, a part is the same as a whole, is true by definition. Products of large infinity that C is larger than Aleph nor is true by definition. But Aleph nor equals 2 to the power Aleph nor by one-to-one pairing, arithmetic proof, by showing a fallacy in Cantor's diagonal argument and Cantor's theorem. I also revised cardinal arithmetic. With this summary, I will resolve other paradoxes in the following discussion. Chapter 2-4, Dimensionality products. Even though it is a common sense Cartesian geometry that we need a set of 1, 2, and 3 coordinates to locate a position in a line, plane, and space respectively, Cantor argued that it can be done by one number because there is one-to-one pairing between a line and plane or space. Space-filling curves further supported the argument, but I showed that there are flaws in the proofs, thus resolving these paradox. I show the fallacy in the Cantor's proof. Cantor's proof is remarkably short in contrast to other long proofs I showed you before, so that it seems impossible to have an error in this very short proof. Let xy be an element in the unit square and z be an element in the unit interval. For any x, which is 0.x1, x2, x3, y, which is 0.y1, y2, y3, there is a unique z, which is 0.x1, y1, x2, y2, x3, y3, Thus, there is a bijection between x and y and z, which is unit square and unit interval. Cantor's remark, "I see it, but I don't believe it," in his letter to Dedekind, is generally taken as, "I have a proof, and therefore know it is true, but nevertheless find it hard to believe." However, Professor Gouveia looked at the circumstances and context of this remark and argued. This remark pointed to Cantor's worry about the correctness of the proof. Yes, Cantor's worry was right. Basic assumption of the Cantor's proof is any real numbers can be written as an infinite sequence of digits. However, we need to ask how long is the digit. Tacitly and without discussion, the length has been considered as Aleph nor. However, I showed that the digit length in real number line in the real numbers is larger than Aleph nor in chapter 2-2. Rational numbers can be written in digit representation by the notation rule, but irrational numbers cannot be written in digit representation, like irrational numbers cannot be written as p over q for any natural number p and q. Therefore, there is a fallacy in the Cantor's proof. We cannot complete the bijection in digits because irrational numbers cannot be written in digit representation, or the digit length of irrational numbers is larger than countably infinite Aleph nor, so that countably infinite Aleph nor number of one-to-one pairing cannot cover the whole digits. In the piano curve, the tacit assumption is that any real numbers, rational or irrational, can be expressed in the base 3 number system with digit length of Aleph nor. But herein, I'll discuss geometric representation of the piano curve. The piano curve is supposed to fill the space, meaning that every point in the plane is in the line. However, suppose a horizontal line in red across the intersection as in figure. Then, element in the x of the intersection is x, which becomes a natural number when multiplied by 3 to the power I. In order for the piano curve to fill the space, all numbers in the horizontal line have to be within x. However, there are some numbers that cannot be an element of x. For example, 1 over 4 is not a multiple of any power of 1 over 3, thus cannot be an element of x. Likewise, 1 over m or its multiples, where m is not 3 to the power I for any integer I, is not an element of x. Irrational numbers cannot be an element of x. Suppose n is an irrational number so that it is not p over q for any natural number p and q. Assume that n is an element of x. Then x multiplied by 3 to the power I is a natural number. Then n equals p over 3 to the power I for some p. As 3 to the power I is a natural number, it contradicts the assumption that n is not p over q for any natural number p and q. Thus, irrational numbers cannot be an element of x. Therefore, there has to be some, in fact, infinitely many numbers that cannot be an element of x, meaning that there are some points in the horizontal line that are not filled by piano curve. This reasoning rejects that piano curve is space-filling and proves that the number of points in the unit square is larger than the number of points in the unit interval. The key in the proof that Hilbert curve is space-filling is that the distance between any point in the subsquare and the nearest point in Hilbert curve of that subsquare becomes 0. The maximal distance between a point xy and the nearest point in the line fn in the subsquare, as denoted fn minus xy, is square root 2 multiplied by 2 to the power minus n plus 2. As n becomes large, the distance becomes smaller. There can be n satisfying square root 2 multiplied by 2 to the power minus n plus 2 smaller than epsilon or any arbitrary small epsilon larger than 0. Thus, fn minus xy is equal to or smaller than epsilon for any arbitrary small epsilon larger than 0. Because epsilon can be arbitrarily small, fn minus xy becomes 0. Therefore, the distance between any points in the subsquare and Hilbert curve in the subsquare becomes 0. Thus, they are equal. However, there is a fallacy in the concept of arbitrary small epsilon larger than 0. For any n, we can find a smaller epsilon larger than 0 that satisfies square root 2 multiplied by 2 to the power minus n plus 2 larger than epsilon larger than 0. Thus does not prove that the distance between any points in the subsquare and Hilbert curve in the subsquare becomes 0. There are three arguments against that Hilbert curve is space-filling. The first argument is the short distance between the boundary of the subsquare and Hilbert curve within the subsquare is 2 to the power minus n plus 2. However, 2 to the power minus n plus 2 does not become 0 because we can have epsilon larger than 0 for any arbitrary large n satisfying 2 to the power minus n plus 2 larger than epsilon larger than 0, proving that there are points that are not filled by Hilbert curve. Argument 2 is 1 over 2 to the power aleph null equals 1 over aleph null. If 1 over aleph null equals 0, then 1 equals 0 multiplied by aleph null. However, in chapter 2-2, aleph null multiplied by 0 equals 0. Therefore, 1 over aleph null is not equal to 0. Because aleph null is a cardinal number, aleph null and 1 over aleph null cannot be a negative number. Thus 1 over aleph null is larger than 0. Thus 1 over 2 to the power aleph null is larger than 0. Argument 3 will be found in chapter 2-5 using Lebesgue measure. Therefore, the above discussion on both space filling curves shows that there is no one-to-one pairing between a line and a plane, thus resolve the dimensionality paradox. The Euclidean length of Hilbert curve after nth iteration is 2 to the power n minus 2 to the power minus n. Thus, the limit length of Hilbert curve is 2 to the power aleph null. Then the number of points in Hilbert curve is c multiplied by 2 to the power aleph null, which is 2 to the power 2 is c multiplied by aleph null equals c. Because Hilbert curve is not space filling, c is smaller than c squared and is consistent with cardinal arithmetic that was discussed. Paradoxes in Cantor set are: Cantor set has 0 length, however, it has infinite number of points within the set. There are 2 ways of measuring the length of Cantor set. Method 1 is by subtracting the total length removed from the total length. Method 2 is by calculating the limit length of Cantor set after ith iteration. Both relies on the calculation of 2 over 3 to the power of aleph null, which was shown to be larger than 0 in chapter 2-3.2 and chapter 2-4.3. Argument 3 that 1 over aleph null or 1 over 3 to the power aleph null is larger than 0 comes from measure theory. In measure theory, any open or closed interval a and b of real numbers has the length b minus a, which is called its Lebesgue measure. If b is not equal to a, then the length is larger than 0. The length of each interval in the Cantor set is 1 over 3 to the power aleph null, as you can see here. Because we are always deleting the segment with the last digit 1 on the left and 2 on the right, the last digits of the left and right endpoints of each interval are always either 0 and 1 or 2 and 0 and are never the same. Therefore, the length of the interval, which is right endpoint number minus left endpoint number, is not equal to 0 because right endpoint number is not equal to left endpoint number. Thus, 1 over 3 to the power aleph null is larger than 0. It is easy to show 1 over 3 to the power aleph null is equal to 1 over aleph null. Paradox of Cantor's function and Devil's staircase is resolved because Cantor set, where there is a non-vertical increase, has a length larger than 0. Vitali set. The key in the proof was that infinity multiplied by lambda v should be between 1 and 3. However, if v is measurable, lambda v has to have a certain number, but if lambda v is 0, then infinity multiplied by lambda v equals 0. If lambda v is larger than 0, then infinity multiplied by lambda v equals infinity. Therefore, lambda v cannot be either 0 or larger than 0. Therefore, it contradicts the assumption that v is measurable. But let's examine the nature of infinity carefully. Infinity in the calculation is the size of rational numbers within minus 1 and 1, which is aleph null. As v is generated by picking one number from each subset, which is aleph number of elements, we can calculate lambda v as 1 over aleph null. Therefore, infinity multiplied by lambda v equals aleph null multiplied by 1 over aleph null equals aleph null over aleph null. Aleph null over Aleph null is not determined, as in chapter 1-3.2, so that it can have a value between 1 and 3, thus does not necessarily lead to a contradiction, meaning that V can be measurable. And let's examine the nature of infinity more carefully. Infinity was the number of rational numbers between minus and 1. Lambda V was 1 over number of rational numbers within 0 and 1. Thus, infinity multiplied by lambda V equals number of rational numbers within minus 1 and 1 multiplied by 1 over number of rational numbers within 0 and 1. Thus, this is 2 multiplied by number of rational numbers within 0 to 1 multiplied by 1 over number of rational numbers within 0 to 1. That is 2 multiplied by number of rational numbers within 0 to 1 over number of rational numbers within 0 to 1, and is equal to 2. Thus, summing lambda V infinite times is 2, which is consistent with the required sum, which should be between 1 and 3. Thus, V is measurable. So, lesson from calculating with infinity is we need to know what infinity means exactly when calculating with infinity symbol. For example, digit length in real numbers is larger than Aleph null. Iterations in piano curve, Hilbert curve, Cantor set is Aleph null. Dissecting the nature of Aleph null helps, as in Vitali said. Here is another example of knowing the meaning of infinity is important and helpful. A real number line R is expressed as minus infinity to infinity. And what will be the length in this infinity? If the length infinity in the real number line is C, then the number of points in the real number line will be C, the length, and C, the cardinality of the real numbers in the unit length, equals C squared, which is inconsistent with the result that the number of points in the real number line is C. If the length infinity in the real number line is Aleph null, the number of points in the real number line is Aleph null, the length, multiplied by C, the cardinality of real numbers in the unit length, which equals C, and is consistent with the result that number of points in the real number line is C. Thus, the length of the real number line is Aleph null. The fact that C is not in the real number line gives more meaning to the question of the nature of C as a number, which was raised by the fact that C does not obey the rules of arithmetic. Thus, we should regard C as an idea, something like expressing dimensionality rather than an actual number. The result that the length of a real number line is Aleph null and 1 over 0 equals C gives a logical explanation, or are consistent with y, which is 1 over x when x is 0, is not possible to exist in the y-axis of the real number line. This concept that the length of a real number line is Aleph null and 1 over Aleph null is larger than 0 should be useful when we consider infinity in physics. This very interesting article on physics of infinity appeared in Nature Physics in 2018. Discussion could become more rich with the result that I just presented. I discussed before that the current proof of continuum hypothesis needs to be re-examined because the proof is based on the wrong premise that 2 to the power Aleph null is larger than Aleph null and infinitely many infinities. I do not have a proof, but I want to discuss an idea. Suppose there is A which is between Aleph null and C. A multiplied by 0 will be either 0 or larger than 0. This requires the premise that any set should be Lebesgue measurable. The Vitali set, a classic example of Lebesgue non-measurable set, was shown to be measurable in chapter 2-7. If a multiplied by 0 equals 0, then a is Aleph null, because if a is larger than Aleph null, then a multiplied by 0 will be larger than 0. If a multiplied by 0 is larger than 0, then a is C, because if a is smaller than Aleph C, then a multiplied by 0 will be equal to 0. In either case, a is either Aleph null or C. Thus, the assumption that there is a between Aleph null and C is contradicted. However, this requires to show that any cardinal number of infinite size whose multiplication by 0 is Aleph null, and any cardinal number whose multiplication by 0 is larger than 0 is C. As stated in chapter 2-2, C is not just quantitatively larger than Aleph null, but qualitatively different from Aleph null, like topological dimensionality, and can only be expressed as being larger, that is, C is larger than Aleph null. Aleph null mirrors topological dimension 0 and C topological dimension 1. Therefore, unless we can construct or define a topological dimension between 0 and 1, it is logical to assume that there is no A which is between Aleph null and C. Conclusion. Cantor's biggest achievement is that there is a larger infinity. However, that C is larger than Aleph null is true neither by Cantor's diagonal argument nor Cantor's theorem, but by definition of a point, a line, and rules of arithmetic. These theorems are false and have led to many paradoxes and counterintuitive conclusions. These theorems are proven correct by multiple arguments and are consistent, without counterintuitive conclusions, without paradoxes throughout the book. Some may say that they are wrong by the axioms in the current theory of infinity. But if these theorems are wrong just because of the axioms, then they are correct without those axioms. And I'll be comforted by this quote by Vladimir Arnold. Some axioms, together with other unmotivated definitions, serve mathematicians mainly by making it difficult for the uninitiated to master their subject, thereby elevating its authority. Ludwig Wittgenstein said, "Mathematics is a method of logic, and the logic of the world, which is shown in tautologies by the propositions of logic, is shown in equations by mathematics." If an axiom makes a difference, we have a different system of logic or math, and I would prefer a theory that is consistent and without paradoxes. In this construct are resolved many paradoxes that were very counterintuitive. I hope you apply this construct to resolve other paradoxes that are not dealt here and enjoy the world of infinity without paradoxes. Furthermore, theorems using Cantor's diagonal argument and the premise that 2 to the power Aleph null is larger than Aleph null as a part of the proof will require re-examination. In the Afterword, I outlined how and why I wrote this book. You may want to read my memoir in this website, which will be easy to find. After sending the manuscript to the publisher, I came up with an idea on rational numbers. I could have merged this into the main body, however, I was busy and tired, and this could stand alone after the main body. Thus, I am leaving this as an addendum. We have been focusing on irrational numbers, but not much on rational numbers in this book. But they are close kins, and need to be discussed together. A rational number represents a ratio of two integers, thus is called as a number, defined as a number that can be expressed as the quotient or fraction p over q of two natural numbers, a numerator p and a non-zero denominator q. The decimal expansion of a rational number always either terminates after a finite number of digits or begins to repeat the same finite sequence of digits over and over. Moreover, any repeating or terminating decimal represents a rational number. These statements hold true not just for base 10, but also for any other integer base. However, there is no active discussion how large the natural numbers p and q or finite may be. Consider the set q of rational numbers within the interval in the binary number system. A rational number within the unit interval in the binary number system can be expressed as 0.a b bar. A is a leading sequence of finite number I of zeros and ones. B is a repeating sequence of finite number j of zeros and ones. Then card q, the number of rational numbers within the unit interval, is this combinatorial, and card q becomes 2 to the power k plus l plus 2 when k and l are large. Both k and l can be very large but not infinite by the current definition of rational numbers. If either k or l is infinite, then the number is thought to become an irrational number. K and l do not need to be different. Thus, in order to simplify, let k and l equals n. Then card q becomes 2 to the power 2n plus 1 for very large n. Because n is finite, n is smaller than Aleph null. Thus, card q becomes smaller than 2 to the power Aleph null, which is Aleph null. Therefore, card q is a very large finite number which is approaching but not becoming Aleph null. However, the cardinality of rational numbers within the unit interval is Aleph null. Thus contradicts the current assumption that the digit length ij is a finite number. Therefore, ij should be allowed to become infinite Aleph null. The fact that rational number can have Aleph null number of digits in the leading and repeating sequence is consistent with the fact that irrational numbers have infinite non-repeating sequence of digits because the digit length in irrational numbers is larger than Aleph null. Furthermore, we can reason that the repetition of the repeating sequence in the rational number is larger than Aleph null. The result that the repetition of the repeating sequence in the rational numbers is larger than Aleph null is consistent with y 0.9 bar equals 1 when 1 over 10 to the power Aleph null is larger than 0. Is 0.9 bar 1? There is a very simple proof. 1 over 3 equals 0.3 bar. Then 3 over 3 equals 0.9 bar, which is 1. By covering the lower diagonal half, in the lower left side of the diagram, we have a complete and ordered set of rational numbers between 0 and 1. Because we can have one-to-one pairing with natural numbers, cardinality of rational numbers within the unit interval is Aleph null. And it is obvious that p and q can become infinite from these arrows. How many rational numbers are within the segments of the Cantor set? Cantor set in the base 3 number system is all numbers which have no ones in the base extension other than in the last digit. From chapter 1-5, a number with non-terminating sequence of zeros and twos will be within the segment. There will be rational numbers and irrational numbers among these numbers within the segment. A rational number within the segment will be a number with a leading sequence I number of zeros and twos, followed by a repeating sequence j number of zeros and twos. Then IQ, the number of rational numbers within the segment, will be this combinatorial, and IQ will be 2 to the power k plus l plus 2 when k and l are large. K and l do not need to be different. Thus, in order to simplify, let k and l equals n. Then IQ equals 2 to the power 2 plus n plus 1 for very large n. Because k and l can be infinite, n equals Aleph null. Then IQ becomes 2 to the power Aleph null. The fact IQ equals 2 to the power Aleph null supports that 2 to the power Aleph null equals Aleph null. If 2 to the power Aleph null is larger than Aleph null, then IQ is larger than Aleph null. However, as the cardinality of rational numbers q within the unit interval is Aleph null, IQ cannot be larger than Aleph null. Thus, the assumption that 2 to the power Aleph null is larger than Aleph null is false. Professor Gouvier advises, a proof is not a proof until some reader, preferably a competent one, says it is. Until then, we may see, but we should not believe. As the last sentence of his paper was Cantor surprised. I take his advice to the heart and want you to examine my discussion critically. I admit that my discussion lacks the rigor that professional mathematicians would demand, but should be enough to show the intuition is correct. I believe I at least crossed the road. Finally, I'd like to thank Gresham College, Wikipedia, pbs.org, 3b1b, infinitely, and I'd like to finish with Shakespeare because there is something to speak about infinity.
Attend the lords of France and Burgundy, Gloucester.
I shall, my lord.
Meantime, we shall express our darker purpose. Give me the map there. Know that we have divided in three our kingdom, and 'tis our fast intent to shake all cares and business from our age, conferring them on younger strengths, while we unburdened crawl towards death. Our son of Cornwall, and you, our no less loving son of Albany, we have this hour a constant will to publish our daughter's several dowers, that future strife may be prevented now. The princes France and Burgundy, great rivals in our youngest daughter's love, long in our court have made their amorous sojourn, and here are to be answered. Tell me, my daughters, since now we will divest us both of rule, interest of territory, cares of state, which of you, shall we say, doth love us most, that we our largest bounty may extend where nature doth with merit challenge? Goneril, our eldest born, speak first.
Sir, I love you more than words can wield the matter, dearer than eyesight, space, and liberty, beyond what can be valued rich or rare, no less than life, with grace, health, beauty, honour, as much as child e'er loved or father found, a love that makes breath poor and speech unable, beyond all manner of so much I love you.
What shall Cordelia speak? Love, and be silent.
Of all these bounds, even from this line to this, with shadowy forests and with champaigns riched, with plenteous rivers and wide-skirted meads, we make thee, lady, to thine and Albany's issues be this perpetual.
My lord.
What says our second daughter, our dearest Regan, wife to Cornwall?
I am made of that self-metal as my sister, and prize me at her worth. In my true heart I find she names my very deed of love. Only she comes too short. That I profess myself an enemy to all other joys which the most precious square of sense possesses, and find I am alone felicitate in your dear highness love.
Then for Cordelia, And yet not so, since I am sure my love's more ponderous than my tongue.
To thee and thine hereditary ever remain this ample third of our fair kingdom, no less in space, validity, and pleasure than that conferred on Goneril. Now, our joy, although our last and least, to whose young love the vines of France and milk of Burgundy strive to be interest, what can you say? To draw a third more opulent than your sisters. Speak.
Nothing, my lord.
Nothing?
Nothing.
Nothing will come of nothing. Speak again.
King Lear wanted to hear her love in words, but to Cordelia, words were just void and empty, but her love was real, that could not be expressed or added up by words that were just void. In this time of trial from COVID-19 pandemic, I'd like to share with you a painting titled The Doctor by Sir Luke Fildes in 1887, which shows the personal, intimate nature of medicine. There is a very ill child in the center. The doctor probably does not have a good idea what is wrong, and probably does not have means to help the child, but is giving a concerned, very intimate, personal gaze at the child. But today, I'd like to focus on parents. Father is standing with his hand over the shoulder of the mother, who looks exhausted. There's a dim morning light through the window, suggesting that they spent through the night. From the picture, we feel the infinite parental love. We see it and know it is there, but find it difficult to express in words. Yes, Cordelia loved the father, but knew these colorful words were just empty and could not express her true love. Sadly, by the time of his writing in 1606, there is no concept of a sea describing or defining the real. Therefore, I thank Gresham College, Wikipedia, PBS.org, 3v1b, Seed Times, because they had me make something out of nothing. This is a book documenting why and how Korean alphabet is created in 1443 out of nothing. Korean alphabet is what defines Korea, like C is what defines real number. Thank you very much.